If you haven't been here for this whole series, I'm sorry. And I can't do much reviewing tonight because we have lots of other things to do. So I'm going to move ahead. You can go listen to the previous lessons if you'd like. And probably you're thinking you've been fed with a fire hose anyway, so you need to read them, listen to them again. And there's plenty of things to think about. My hope in a series like this, because I know very well most of you aren't going to remember 9/10 of what I said, and I don't expect you to. What I expect you to do is love God more than ever and appreciate His majesty. And if that much is accomplished, we will have spent our time well. So I thank you, especially those of you that have been here every time. I've been around a long time, and I know that 3 of these is about all folks can handle in a given circumstance. I used to do 5 of these or 6 in a row, and you've lost your audience. So 3 is enough, and tonight we're going to finish with this topic, molecular machines. Folks, 10 years ago, we knew almost nothing about molecular machines. So what we're talking about now is very current information, and it's a lot about which we've learned and still are learning, and I hope it'll be enjoyable to you to see just a piece of this general topic. So that's my introduction tonight. We're going to start again with our theme passage for this whole series in Romans chapter 1 and verse 20, which says, "For since the creation of the world, His invisible attributes are clearly seen, being understood by the things that are made, even His eternal power and Godhead, so that they are without excuse." I do want to read one more verse here. "Because they knew God, they did not glorify Him as God, nor were thankful, but became futile in their thoughts, and their foolish hearts were darkened." And the rest of Romans 1 is describing what happens when people give up on God. And it's a horrible picture. And you and I have watched it in our generation, even in the United States of America, as we've watched things unfold before us morally that we never would have believed. And it's because, in large measure, we've left God behind. But I don't want to do that tonight, nor in this series. So we're going to make the argument from design again this evening, and my question to you will be, what's more reasonable, that the things we're going to talk about tonight happened by natural causes over millions and billions of years, or that they were designed by a magnificent, powerful creator? I think the answer is obvious, but I'm happy to share with you some information leading to that. All right, I've mentioned this book to you. William Paley's Natural Theology, taught to every college student. That theme was in every college. Everybody took that class. And you learned the evidences of the existence and attributes of the deity, collected from the appearances of nature. And based on what he knew, he had a whole book worth of information of what you can discover. That was in the early 1800s. We're in 2025, folks. And since 1950, we have learned more about the evidence that is in nature for life than everything Dr. William Paley and all the others knew prior to that. So I want to introduce you now to Richard Dawkins. We've mentioned him several times. I'm going to use a little bit of a reference from him from this book, The Blind Watchmaker. The watchmaker argument is, if you found a watch out on the streets or in the heath as he did, and you picked it up, you would surely say, somebody made this. And he proceeds then to make the argument, when you look at nature, there are many things much more complex than watches that surely would lead you to think somebody made this. Well, Richard Dawkins makes a play off of that book, as you'll see. So I want to just share with you a few things from this book. It was a bestseller, folks, and Richard Dawkins is one of the 4 horsemen of the apocalypse, of the new atheists. He's an outspoken and blunt and sometimes not very nice evolutionist. He starts his book this way: "Biology is the study of complicated things, things that give the appearance of having been designed." All right? Nobody disagrees with that. Everywhere you look in biology, things look like they've been designed. So he admits that on page 1. I go on and skip over to page 3. The process by which an airliner came into existence is not fundamentally mysterious to us. Humans built it. Would you say amen, class? Nobody's going to argue with that. The systematic putting together of parts to a purposeful design is something we know and understand, for we've experienced it firsthand, even if only in our childhood and building erector sets. What about our bodies? Each one of us is a machine, like an airliner, only much more complicated. Were we designed on a drawing board too, and were our parts assembled by a skilled engineer? The answer is no. It's a surprising answer. And we've known and understood it only for a century or so. He says we didn't understand it until Darwin. Then he says this: the watchmaker of my title is borrowed from a famous treatise by the 18th century theologian William Payne. His Natural Theology, published in 1802, is the best known exposition of the argument from design. Always the most influential of the arguments for the existence of a God. It is a book I greatly admire, for in his own time its author succeeded in doing what I'm struggling to do now. He had a point to make, he passionately believed in it, and he was, let me find it here, he spared no effort to ram it home clearly. I want to say those again. He had a point to make, he passionately believed it, and he spared no effort to ram it home. He had a proper reverence for the complexity of the living world. So do I, says Richard Dawkins. And he says, I'm also passionate, and I also ram mine home. So folks, I'll make no apology for screaming and yelling sometimes to make the point and drive it home, because our opposition does it all the time. And being passionate about things, I hope you've noticed I'm a little passionate. And it's for a purpose. I'm convinced that we need to be passionate about the existence of God and the evidence that's overwhelming for that. Paley's argument is made with passionate sincerity and is informed by the best biological scholarship of his day. But it is wrong, gloriously and utterly wrong. An analogy between a telescope and an eye, between a watch and a living organism, is false. All appearances to the contrary, the only watchmaker in nature is the blind forces of physics, albeit deployed in a very special way. Now, did you get that? This man, in his blatant, passionate, ramming home, says the only thing you need to produce everything we see is the blind forces of physics acted upon by natural selection. Folks, I'll say it again, I've not seen such faith in all of Israel. Natural selection, the blind, unconscious, automatic process which Darwin discovered and which we now know is the explanation of the existence and apparent purposeful form of all life. It has no mind, no mind's eye. It does not plan for the future. It has no vision, no foresight, no sight at all. It can be said to play the role of the watchmaker in nature, if you can call it the blind watchmaker. And so he then proceeds on 300 pages to try to convince you that everything you see that sure looks like it was designed was not. And that all was involved is the blind forces of physics with this blind watchmaker, natural selection. And I have to read you one other piece here, just unbelievable. I'm now reading from page 13. In his beautifully written book, The Creation, the Oxford physical chemist Peter Atkins begins this way, and he quotes Peter Atkins. This, folks, is a prize-winning chemist. So please listen closely. I shall take your mind on a journey. It's a journey of comprehension, taking us to the edge of space, time, and understanding. On it, I shall argue that there is nothing that cannot be understood, there is nothing that cannot be explained, and eventually, and everything is ultimately extraordinary simple. A great deal of the universe does not need any explanation. Elephants, for example. Once molecules have learned to compete and create other molecules in their own image, elephants and things resembling elephants will in due course be found roaming around the countryside. I want to do this. You don't need to explain elephants, class, says this physical chemist. Once molecules learn how to produce themselves, you'll find elephants walking around. I'm sorry, that's what we're dealing with. All appearances to the contrary, the only watchmaker in nature is the blind forces of physics, albeit deployed in a very special way. Natural selection, the blind, unconscious, automatic process which Darwin discovered, has no purpose. It's the blind watchmaker, and that is what they believe with all their heart. And that's the only watchmaker you need. So, class, I'm asking you tonight, when we get finished with what I say to you tonight about molecular machines, is it more reasonable to take that as your answer? Or that there was some grand, immeasurably powerful being that made it? I say it's time to revisit the argument from design. And I mentioned to you this morning that there's 3 discoveries in this century that cause us to think that. There's a beginning, the universe is fine-tuned, and even the simplest forms of life have a massive amount of information. And class, there is no evidence that you get information from any source other than an intelligent source. Period. But there's information everywhere you look, stored inside of every living thing and being used for phenomenal things at an amazing rate. So these 3 things say to us, you need to be thinking about a designer. So here's a quote from Darwin's book. I have a copy of it here. Darwin's On the Origin of Species. You can see my copy is pretty well worn, and I will tell you, my view is that this book has had more impact on humanity than any other book except the Bible. And it's not a good impact, because it has changed the worldview of many, many people and dismissed God. But I'll tell you one thing I've learned from looking at this book. Darwin was a man who was willing to critique his own theory. You will find many statements in here saying, here's what's wrong with my theory, or here's how you could critique it. Here's one. If it could be demonstrated that any complex organ existed which could not possibly have been formed by numerous, successive, slight modifications, my theory would absolutely break down. Why does he say that? Because he would tell you in this book, nature abhors leaps. In other words, we don't see anything in nature like you have a bird, he lays an egg, and it comes out to be an elephant. That doesn't happen. But he does believe you can start with something like a single-celled organism and eventually end up with an elephant by small, successive changes over long periods of time that add up. So his theory is absolutely dependent on what you just saw here. So can we present an organ that could not possibly have been formed that way? Well, in the first place, the way he presents his argument is really not fair, because he's asking you for something. Can you do something It could not have happened this way. Well, could you make up a story about how it could have happened? And a whole lot of his book is making up stories about how it happened. The fact I'm going to ask you is, class, you look at this organ and think of all that's required for it to be functioning, and you tell me that could have happened without all of it being there at once. I showed you one this morning, didn't I? You need it all, or it doesn't work. So at least he critiqued himself. So I want to present to Mr. Darwin, and by the way, if he were alive today, I'm going to give him the credit that I think he would have given up his theory had he been here today. Here's one. How about the cell? You know what was said about the cell in the 1800s? It's an albuminous blob of carboniferous material. They thought it was just a blob. And folks, it's pretty easy to believe that a blob could come into existence by itself. But if he knew what that blob was made of, what we know today, that blob, class, has more information in it than you put all the cities, the largest cities in the world together today, and their complexity and all that's going on in them. There's more going on in that. We call it a self-replicating nanoscale robot. I finished with that this morning. Self-replicating because it can reproduce itself. Class, I didn't show you the video where the cell reproduces DNA. I'm not going to take the time tonight, but I'm going to show you something else. But did you know that in your body, every cell in your body reproduces the DNA that makes you who you are all the time? And it makes perfect copies. And if there's some, by chance, for some mechanism, there's a mistake in it, it has a correction process to help fix what was wrong. Did you know that? Yes, your DNA is copied all the time. It's self-replicating. Everything in your cell is reproduced. It's a nanoscale because it's very, very small. And it's a robot because its activities are carried out unconsciously and automatically by precision molecular machines that follow ordinary physical laws. And that's some of what I want to illustrate to you tonight. So what's a molecular machine? Please note, class, a natural device on molecular scale with few exceptions made of protein. Exactly right. You're not getting away from that. Because molecular machines, class, are mostly proteins. And they're doing work all the time. Very busy little creatures. They can convert chemical energy to produce linear or rotary motion, as well as controlling many biological functions that you're doing all the time inside your body. So I introduce you to myoglobin. It's an oxygen storage machine inside your muscles that allows you to keep using them. I wish I had time to talk to you more about that, but we're going on to kinesin and dynein. Kinesin walkers, they call them, are for cargo movement and cell division. If you want to have some fun, maybe not tonight, you're going to be tired when you get home. There is a video you can watch called A Day in the Life of a Kinesin Walker. It's a cartoon. And it's showing you all the work that Kinesin walkers do. They're very busy little people, little things. But they do important jobs, and I'm going to show you one in a minute. And dyneins involve the beating of cilia and flagella and cell division. They're involved in all of this very intricately. So here's a picture of a kinesin walker. It's this little guy right here. That's a, what do you think, class? A protein, yes, a rather extended one. You notice he has feet, and he walks along microtubules, which your body builds. And he walks along carrying enormous pieces of things that need to move. This blob you see him carrying probably weighs 100 times more than he does. He's carrying it. And I have videos of little kinesin walkers walking along. And I can tell you, if we had the time, I could explain to you the chemistry of how he makes every step. We know exactly how he does it. It's regular physical properties. It's a machine class that does work for you all the time. Lots of movement going on. So let's talk about one. Here's our first video clip for tonight. Are you aware? Let me get my statistics here, because I don't carry these numbers in my head. By the way, while we're on this little break, I want to mention 2 more books to you. Darwin's Black Box by Michael Behe. Don't get the earlier edition, which was in 96. There's a 10-year later edition, 2006. Update. And then, What Darwin Didn't Know, Jeffrey Simons, MD, former atheist, became a believer because he's a doctor, medical doctor. All right, some statistics. Cell division. Now, let me just ask this of you, class. How many times in your body do you think, let's put it another way, how many cells die in your body every day? You want to take a guess? You say millions. Anybody else? All of them? Not in a day now. You'd be in trouble if they all died in a day. No. Approximately how many cells do you have in your body? Depends on who you talk to. 13 trillion. Some say 30 trillion. Maybe millions is right. This says 50 to 70 billion every day. You got a lot of death going on inside of you. How about your skin? You lose 40,000 skin cells every minute. They die. Now, in the case of your skin, they die and then they stay and they kind of make layers of your skin. Did you know your skin has a bunch of layers? And the top layers are mostly dead because it helps protect you. Women don't like it because it's not soft and smooth. But you need dead skin. You got a lot of death going on with skin cells. 40,000 per minute. How do you produce new ones? Down at the base, they mitosis. That's what we call it. It's cell division. So that one cell becomes 2 cells. And we're going to watch it happen right here. Now, the first part of this video clip is an actual live shot of what's happening to the DNA. You're going to watch it. The next one is Drew Barry, our favorite animator, making an animation of what goes on down at the nano level. And that's what I want you to see. I want you to see both. So my expert IT guy in the back. May I stop and say, will you please help me thank him later? You just hug him. Everybody hug him. And hug his wife too, because she's been helping him. But John's been great. And he's going to help me again with this video. John, let's get started. Let's watch this live cell. And Drew Barry has done such a nice job here. So watch. This is the nuclear material. These are the chromosomes. Stop just a second there. Before this ever started, the DNA has already been copied. So I'm not showing you that. Folks, that's incredible. And watch me. How fast did it happen? The DNA is copied that fast. So that's already happened. So we've got 2 copies of the DNA here now that are starting to spread out. All right, here we go. Go ahead. You can see it's spreading out. There's phases it goes through. Mitosis has several phases, and you can learn that in your biology classes, I expect. But you're watching it here now. It happens, and then eventually they pull apart here, see? And one cell becomes, stop right there, becomes 2 cells. What you've just seen is amazing. Because this cell and this cell are identical. They're exact copies. So that where you had 1 before, you now have 2. You better have that going on or you're going to die. Mitosis is critically important to your living. And you can't have mitosis without molecular machines. So next, here's what we're going to do. We're going to watch this again, only instead of looking at the whole thing, we're going to focus on one chromosome. So watch. See, here's the same DNA material splitting apart. And we're going to focus in on this one right here, that chromosome. So stop right there just a minute, John. Can you see there's already 2 copies, class? There's one in the back and one in the front. That chromosome's already been copied. You see these little lines coming out? Those are microtubules extending out from it. So we're going to focus in on this one, and we're looking at the metaphase right now. Let's go on. And this is now beginning our animations by Drew Barry. And he likes to color things. Just forget the colors. They're there for a reason, but they're not the colors of anything. 2 copies are there, and we're going to focus in on this particular thing. You see this darkish red? That's the kinetochore. And that's because kinetic means what? Moving and active, and the kinetochore is where the action takes place. So stop right there just a minute. This is a giant molecular machine that controls chromosome movement. And what I'm going to tell you is not just one, it's a machine made up of a bunch of machines that are all doing important things that allow your cells to divide, folks. This is way down at the nano level that nobody sees, of course. You're not able to observe down that low unless you have specialized equipment. But here we go. Let's watch. We're going to focus in here because what's happening there at the kinetochore is a lot of activity. Now we're expanding that bigger. This is the kinetochore. He's got it colored red. Stop right there. We've got microtubule attachment. You see, these are all the microtubules. They are being constructed, class, out of what do you think? That's pretty good. What are they being constructed out of? Proteins, by proteins working on that end. And I want to tell you, way over here, at the end of the pathway of that microtubule, they're tearing it down and getting rid of it just as fast as you're building it, like any good government. But the reason is, if you left all those microtubules inside the cell, it would get so clogged up with walkways, it couldn't function. So they are torn down and recycled. So you can use them again. All right, so you got proteins helping to build this protein walkway because there's stuff that needs to go back and forth in order to allow this thing to move and separate into 2 different cells. Now you're going to watch, because in this red area, which is not red, class, it's red because that's where the stuff's happening. And there's a lot of activity going on in here, most of which I'm not telling you. All right, go. But one of the things happening is there are proteins in here that keep time and that allow you to know when is it right now to start that division process, and he's going to do it by turning this all green. You watch. When it starts turning green, that means they've turned on the time to say it's go time, folks. A lot of activity happening there. See the green? Now, stop right there just a second. What's going to start happening is those walkers and other things are going to start moving up and down the microtubules. So you watch. There's going to be some microtubules with walkers on them. Go. Here come the Dynein walkers, headed right out this way. You see all the way up and down here? And stop right there. Can you see this guy going the opposite way? That's the kinesin walker. Kinesins always go this way, and Dynein walkers go this way. Don't ask me why. That's the way it is. And they're busy doing the job they are designed to do at a very high rate of speed. And you see these little guys? That's another, what do you think, class? Protein that helps keep the microtubules in the state of order and allows these walkers to take place. Let's watch this little guy here for just a minute. Watch him walk. See this? Stop right there. Every one of those steps is a chemical process that allows him to carry this important glob of, what do you think, class? Proteins and other stuff from one end of that microtubule all the way over to the other one. And he doesn't do it that way. May I show you what he does? It's fast. All right, go. And when the time is right and they've delivered the appropriate packages to the right place and done the right combination of things about which we could describe chemically but will not, then we go back to the big picture And here at the kinetic core, it now begins to say it's time, and all the proper processes have taken place, and now we can split it apart. And out of one cell, we end up with 2 cells. Stop right there. I feel like I did a completely inadequate job, because you ought to be falling on the floor. Folks, it's incredible what just happened. That happens in the billions of times every day in your body. And especially in your skin, kids. That's why you need to take a bath. Skin comes off, and you don't want to live with that. And neither does your spouse or your person that loves you. So little kids back here, are you listening to me? You have to take a bath, because you got a lot of dead skin on you. You get rid of it, and your body's replacing it incredibly. All right. I think that's enough on that one, isn't it? Are we done? Yeah. Now let's talk briefly about cilia. Anybody know what a cilia is, or a cilium? It's a little hair, and they kind of fly like this, wiggle around. Do you have any idea how important one hair is? Well, you lose a bunch of them up here. And we know the Lord knows every hair, right, that falls. He also knows you got lots of other hairs besides here. You know you have a lot of hairs inside your body? You do. And I don't want to talk about some of them. But you have some in your nose, don't you? Yeah. Where's another very important place where you have hairs? Your ears is important, but there's a more important place than that, inside. The digestive tract has some, but there's an even more important place, because you can die if you don't have these hairs. Your lungs. Yeah, so I have a picture here, I think. Yeah. Here's your lungs. See this primary bronchus right here? That thing is full of these. That's little hairs doing this. What are they there for? They're to keep stuff that doesn't belong in your lungs from getting in your lungs. Now, they're not 100% effective, especially if you smoke or other things that destroy the cilia. But are cilia important, class? Do you know that your body has to construct every one of those? And we know how they're constructed. And it takes Keynesian walkers and Dunedin walkers, in addition to other things, to build every hair. And so they'll walk out as the hair is constructed, one little piece at a time, out to the end, and then others will be walking back this way, and you go back and forth with the appropriate delivery system, and you build hairs. That's happening all the time. And it's life or death, class, in many respects. So you've got cilia that are critically important, back up, in lots of places on your body. I wish we had time to show you the chemistry of cilia building, but we don't. Because I want to get on to the last one today, which is the bacterial flagellum. And I'm going to conclude this series by hopefully describing to you successfully the amazing bacterial flagellum. When I first did this, my Marilyn was sitting in the class, and she said, "Sweetheart, you lost me after your first sentence, and you didn't make it come alive. You got to fix that." So class, I'm making this come alive. Right? We have a video. And we're going to start the video, and John, you be ready. Go ahead. Stop. That's a little bacteria swimming around. You see it? And he's a pretty good swimmer, but he's not a really good one. But you see this little, that's his flagellum. It rotates. and allows them to swim. Let's watch a little longer here. That's one kind of bacteria right there. But there's a better one. Watch him coming up here. This is a live shot, by the way. Here comes another one. Look at these guys. Stop. That's an E. coli, class. You familiar with E. coli? What's it good for? How about killing you? That's something it's good for. But did you know there are strains of E. coli you can't live without? And you have thousands of them in your intestines. So I'm making this come alive. Right now, as you sit there, these guys are swimming in your intestines. Are you with me? And if you didn't have them in your biome, you'd be dead. They are not you, but they are in you. You're giving them a favor, and they're giving you a favor. So why is it we know so much about the bacterial flagellum for something like E. coli? It's the most studied bacteria on the face of the earth because it can kill you if you get the wrong one, and it can help you if you get the right one. So we want to know a lot about this guy and how he works. In the first place, you saw how fast he's swimming? Most of those little E. coli have 4 flagella, or sometimes 10. And they wrap around each other, and then they rotate. So it really allows them to go fast. So what I'm describing to you right now, please keep this image in your mind, is these little creatures swimming inside your intestine. I know that's not a happy image, but you need it to keep this real. Here's the second thing. I want everybody to look at your thumb sideways. Look at your thumbnail. Kind of hold it out like this. The width of your thumbnail. You could line up 1,000 bacteria E. coli across the width of that thumbnail. Are you listening? Are they tiny? Yeah, they're tiny. And these little creatures that make a difference in your life, that tiny, have what I'm about to describe you on them. That keeps them functioning and keeps you alive. And we know more about this machine than any other one. So my job is to get across to you how effective this machine is. So first, I want to quote you from a Harvard professor by the name of Howard Berg, who is an international expert biophysicist, and he's an expert on this particular machine. Here's what he says. It is the most efficient machine in the universe. That's the quote. Here's why he says that. It has a motor in it that rotates, which I'm going to show you in a minute. It rotates anywhere from 6,000 to 17,000 RPMs. Somebody that's in engineering, tell me what RPM means. Rotations per minute. That machine that we're going to show you rotates up to 17,000 rotations per minute. The last time I did this, I had an engineer call me and say, I've got some interesting statistics for you about racing cars. He said the F1 cars RPM is 15,000 RPMs for the best racing cars. And electric generators have an RPM of 1,800 up to 3,600. That's generators that we build. This little motor and that little old tiny bacteria rotates faster than any of those, way faster. But here's the thing. It takes almost no energy. Did you hear me? It uses an acid imbalance across the stator. And I'm not going to go into all that. I don't understand a lot of it myself. But the way it generates the energy that allows it to rotate that fast takes almost no energy. If we could figure out ever how to do anything near to that, we'd never have another energy problem in our lives. But a little bacteria doing it all the time. But here's the other thing. When that machine rotates up to 17,000 RPMs, the filament that it drives goes up to 1,000 RPMs. That's 17 times per second. Can't even do it that way. The motor up to 283 times per second. And here's the other remarkable thing. When it's rotating clockwise, it goes a certain direction. When it's rotating counterclockwise, it turns another direction. And that little motor can go from forward direction to reverse direction instantaneously and go from 17,000 in one direction to 17,000 in the other direction in almost no time. No wonder Howard Berg says this is the most efficient machine in the universe. We don't know anything like it. This thing travels up to 60 cell lengths per second. A cheetah travels 25 body lengths per second, 25 times its body length per second. This little guy travels 60 cell lengths per second. That's way faster than a cheetah. Okay? Have I gotten this across? Folks, this is the most remarkable machine you'll ever want to talk about. And we cannot produce it. We haven't touched it. All right, let's go. Whoops. See, I messed you up, John. But we're back. We're close to the front anyway. Keep going. So here's E. coli swimming around at a magnificent speed, zipping around there. And this little flagellum motor going crazy. So now we're going to start the animation. And here's your bacteria. This is the bacterial flagellum coming out of it. Let's just say, stop right there. That's an E. coli. And here's the flagellum coming out of it. And what I want to do now is describe the parts. So watch closely with me. Here's the, go ahead. Go ahead, John. All right, you're going to see the word here in a minute. That's the filament. And that's the hook. Stop right there, John. The filament, can you see that's a different color, class? Why is that? Because that's a different protein. Do you notice in between them there's some different colors? That's different proteins. And here the hook filament is different colors, so that's a different protein. Here's something you need to know. This hook that connects the motor to the filament is critically important. And what we've learned is it has to be exactly 52 nanometers long. That means there have to be the exact right number of protein elements joined in here to make this work properly. How does that little thing know how to make something exactly 52 nanometers long? It's built into its DNA and proteins. Let's continue. Okay, so now we're going down inside through the cell wall here, and you've got to see all these rings. We're going to point out the various parts of this now. This is called the basal body, this whole thing. And it's made up of a rod down the middle, a bunch of rings, and then the rotor down here. Stop right there. Do you see here there's an inner membrane, a middle layer called the peptidoglycan layer, and an outer membrane. That little creature has a skin around it that's got 3 layers. You remember how tiny it is? The skin itself has 3 layers. And there's stuff going on down inside those 3 layers. Very important. You see, like right here, this whole thing is stabilized on the middle layer. We'll come back to that in a minute. But look at all those parts. Every different color means a different. Yeah. There are probably 50 different proteins in this little thing. Go. Now, I think it's where we're going to, let's see, I think we're going to turn on the rotor here. Watch the rotor. This is the stator. Stop there just a second. A stator, you see it's stobbed right up into that middle layer. The stator is what stabilizes something, folks. If you're rotating, do you think it might shake a little bit? Every motor man's ever made that's rotating has to have a stator to stabilize it. Well, this has a stator, and it keeps it from blowing itself up by rotating so fast. So there it is. And it has another function too. It's across the stator that acid imbalance happens to drive it and let it go. So go ahead. Here's the rotor. That's the motor piece of this thing. It's made up of 1, 2, 3 layers with different kinds of proteins. Stop right there. Now here's what you need to know, class. When that little euglena, or the little, thank you, when that little bacteria dies, of course you lose everything, but when it divides, it doesn't produce the flagellum in the division process. So each of the two little new ones have to build a flagellum from the ground up. Built into these little bacteria is the process for constructing the entire flagellum from the ground floor up. You obviously didn't get that. May I say it this way? What an evolutionist has to account for is not only how the most amazing machine in the universe got done and works like it does. How in the world did that happen? By small changes over long periods of time, millions of years. No, that's not all. You also have to explain how the factory that builds it is inside that cell also. So you not only have to build a Ford, you have to build a Ford factory. And you have to account for how that happened. And old Mr. Dawkins would say, no problem. All we need is the blind forces of physics, acted on by natural selection. Small changes over long periods of time. Listen, folks, if Darwin walked in that door tonight and heard all this, I think he'd walk out and say, I give up. And if he didn't, he should. So watch. This video was made by a Japanese company who has studied every aspect of the bacteria's life, including the building of the flagellum once it divides. So here we go. Here's how you build a flagellum. Go. It is constructed, folks, from the bottom up. So you start down here, and you have this fly F protein. There's exactly 20 some odd copies of that, called the MS ring. That's built first. Second, the fly G protein builds this piece. And then the fly M and the fly N proteins build this exact number of copies. And then the rod is constructed up the middle by a different protein. And then it has a cap here that's constructed that allows it to drill through the cell wall. Stop just a minute. You think it's healthy for that little guy to drill a hole in his wall? No, that's the way you kill something. But watch what happens as it drills through that wall. Watch. First you look at the stator, which is going to be built at the same time, that middle piece, but watch it drill through now. Rod proteins and the rod cap are drilling right through 3 layers of skin. Whoop, stop. You see how those 3 things formed immediately? Class, you got this thing driving up through, and immediately, boom, 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 the 3 rings form, and there's a massive amount of chemistry going on right there with those 3 rings. Those are 3 different proteins. Do you see that? All of those proteins are driven up the rod, and they're each formed in order. There is not an engineering firm in humanity that could do anything near that good. But the little bacteria does it all the time. Let's keep going. So now you've drilled through, and you've got the L ring and the P ring, and you dismiss, stop just a minute, you dismiss that other cap because you're finished with it, and guess what happens to it, class? As a protein, it recycles. And you build another cap called the hook cap to construct that 52 nanometer device. Watch, it's going to show you how it builds it. The proteins come up through the middle of this rod, and they're driven out, and here they are. And let's make sure we stop, right? Keep going. There, stop. All right, so we have constructed our hook that's exactly 52 nanometers long. We dismiss the hook cap and recycle it, and then we start producing the right kind of protein to allow it to connect to the filament. So go. That's the first hook filament function proteins. That's the second one. Stop right there. So you've got 2 different kinds of proteins that allow it to hook up here that are just automatically constructed and driven up through that rod and made right as they are supposed to be in the timing that they're supposed to be. Am I wearing you out? Keep going. Next, we build Another cap. Filament cap. Stop right there just a second. This one is so famous it's been given a name. It's called Twinkle Toes. You'll notice she has 5 legs. 1, 2, 3, 4, 5. You see them? And the reason she's called Twinkle Toes is because there are exactly 11 openings around this, and those 5 toes go in alternate ones. And so as she dances around, may I do this for you? Toot, 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 toot. As she dances around, different holes are opened up, and so the protein coming up through it, one at a time, can be funneled off to the exact right position. Does this look like a plan to you? Does this look like somebody designed it? Keep going. Each one of those proteins, that's filamin, by the way, a different protein than anything else, and they come up here one strand at a time, and she guides them into the appropriate place as they form this amazing structure, which is extremely strong and flexible. Watch. Way too slow. Move it. That flagellum is way longer than the protein, than the little molecule itself. You know how many units of protein are in that filament? Up to 30,000. One at a time. I ask you, class, are you stupefied? Don't talk to me about how something like this evolved. I don't want to hear it. There are multiple protein processes going on in there. Each protein is complex and suited for its function. Each machine is highly sophisticated, intricate, dynamic, and elegant. These machines are spontaneously self-assembled. Not only are they better than any machine any man ever built, it builds itself. And there are thousands of them in every living cell. So which is more reasonable, class, to explain the existence of these things? How about this? They were produced by the blind forces of physics through numerous successive slight modifications produced by random variation acted upon by natural selection. That's Mr. Dawkins, the blind watchmaker. You believe that? I got a bridge to sell you. Or is it more reasonable they were designed by a supremely intelligent grand designer? You can't see God by the elements of science, but you can see him everywhere. And the more he's opened up the floodgates, the more powerful the evidence has become. So is it reasonable to believe in God in this scientific age? Ladies and gentlemen, it has never been more reasonable in the history of mankind. And I say to you again tonight, I leave this way. I will go home tonight and ask forgiveness again, because we have not begun to start to let you see the magnificence of what we already know, and we don't know anything about this amazing world that God has made. And I thank you for sticking with me as long as you have, and I think you ought to be respectful tonight. I finished in an hour. Thank you, and I'm going to close this by saying, God bless you, and I do want to lead you in a brief prayer. My mic on? Our good Father, we are so humbled to think about the majesty of what you've produced. And we understand very well that through the centuries, men have not known the kinds of things we've talked about this week and that we've learned only in recent years. And we have so much yet to learn. We understand that. You have created things that we haven't begun to think about. But what we know should certainly bring us to our knees and cause us to know there is an amazing Creator that made not only this world, but specifically that made us in His image as the only creatures anybody knows anything about who can think about how we got here and how there must be a grand designer that is something far beyond and someone far beyond this nature in which we live. So we thank you for the privilege of thinking about it. We thank you for opening the floodgates of information for us that help our faith to be stronger than ever. And may it drive us, O God, to obey you, to learn about your Son Jesus, and to be a servant of yours all the days of our life. We thank you and we praise you in Jesus' holy name. Amen.